friends, in the previous lecture we have discussed what all pollution problems are there in the aluminum industry, from the mining to the leaching, smelting. In every step all kinds of contaminants come out of the system, the solids, liquids, gases, only a tiny fraction of which finds use or we find ways and means of recirculation. The rest remain with question unanswered. As regards gases, we saw apart from CO2, the smelters release many other gases, which certainly has local effect, can have regional effect. They also have global impact, and the one that contributes to global impact of course is CO2, as everybody knows. Let me take that subject now and say one or two things about CO2 emissions. Now, we all know the CO2 emissions from carbonaceous fuels have become a critical subject now. It is increasing at a rate of 0.028% per year. And remember, I mentioned that 400 years ago when Taj Mahal was built, it was around 280 parts per million, it has now come to 380 parts per million. People say if it goes to somewhere near 450 or so, I think there will be catastrophe in this world. There will be too much of global warming. As it is now, temperatures, average temperature of the globe is rising, and in recent conference in Copenhagen, everybody has agreed on one point, that we cannot settle for anything beyond 2 degrees temperature rise. So, all the attempts are being made for fixing the maximum allowable increase to 2%, 2 degrees. Now, I am going to give you some figures from National Geographic March 2009 issue. Some of the figures need some revision, because in Copenhagen the whole thing has been rediscussed, but then changes cannot be too drastic. People cannot say that we promised so much in the past, now we do not want to keep that promise. There has been some confusion, of course, because the Kyoto Protocol 5 years ago was based on certain principles. I mentioned that before, and the principles were that the advanced countries will cut down their CO2 emission, whereas developing countries would be allowed to increase their CO2 emission, but at a reduced rate, so that they come to certain level of development, and eventually all countries should have the same per capita emission. People are not agreeing to this per capita basis anymore. Advanced countries are saying no, it should be country wise quota. But then India, China, Brazil, South Africa, they have resisted this. Let us discuss it little bit now. Now, the carbon emission target, reaction targets for different countries as of now are the following. This is as per National Geographic 2009, not legally binding, but commitments from the government. The US says it will cut down by 17% of 205 levels by 2020, means by 2020 they will come to a figure less than, which will cut 2005 figures by 17%. But actually when they promised this some time ago, they have gone back on their promise. They are not cutting down, they are increasing, but they promised to cut it by 30% by 2030 and by 80% by 2050. All reference to 2005 is the reference point. European Union says that it will bring down the CO2 level to 20 to 30% of 2005 levels by 2020. Brazil says 36 to 38% by 2020. South Africa 15 to 20%, Indonesia 26%. India did not have a set target early in this year, but they are also saying 20 to 22% cut by with reference to 2005 level by 2020. But now this is a Herculean task, because see, the present annual growth rate of carbon emissions in percentage is 25% for US, is growing per year by 25%, and they are talking about cutting it down to the level less than the level at 2005. Canada 54, Japan 17, Germany 18, India 97 and China 109. Now, India and China, the fastest growing economics in the world, are under attack by the developing countries because of this very large figures of 96 and 109, which is the annual growth rate of carbon emission. Every year it is doubling. But what we need to see is, if you do it by per capita basis, it is far smaller compared to US, Canada, Japan, Germany, etc. Our population is large, and they have to be brought to a certain level. So, we have to consume more energy. Unfortunately, power is coming from thermal power plants. So, we are emitting more CO2. In UK, somehow the rise is only 1% annual growth, and Russia it is negative, because it was very high at one time, it is negative now. These are not my figures, I am taking it from National Geographic 2009. Now, the two new words have become very important today, and you must know these words. One is carbon footprint, that is carbon consumption by an individual required to maintain his lifestyle. How much carbon are you consuming? Of course, not just in terms of food, mostly coming from transportation. How much fuel you are consuming for your transportation? If you are going by air, imagine how much fuel you are consuming. Whatever energy you are using in the air conditioner, in lighting, for your personal lifestyle, that all goes to give you a carbon footprint. So, I know of a manager, he was the chief executive of Manganese Ore India Limited. That company is very sensitive about this emission problem, and I will tell you what they have done about it, but he calculates his carbon footprint, and every time he takes and travels by air, he feels very guilty. He said, I know my carbon footprint is increasing. See, carbon footprint of a villager in a village is almost nothing. He does not consume carbon. His lifestyle is not at all injurious to global warming. But those of us who are enjoying a different kind of lifestyle, we have carbon footprints, and those who are more prosperous in power, carbon footprint is enormous. Then there is another term called carbon credit. Carbon credit is acquired by minimizing carbon consumption. So, if you are running an industry using a traditional source of power, if you can go for an alternative source of power and save on carbon consumption, you get carbon credit. 1 ton of CO2 saved is 1 CER, certified emission something, and this can be traded with somebody not doing so in exchange of financial gains. If one company is not able to reduce and he is being pressurized to reduce, he can buy, he can pay money to those who have saved. So, there is an exchange of the carbon balance. As I said, it does not overall bring down the carbon credit, carbon CO2 emission, but the polluter is being financially punished and one who is doing better is financially rewarded. That is the system based on which carbon credit works. So, this is one way of rewarding cleaner operation and punishing the polluter, but it does not solve the problem. Please remember that it does not solve the problem, it certainly helps. Now, I referred to this company called Manganese Ore India Limited. They are ferromanganese producers, and ferromanganese is produced, I have talked about that in electric furnace smelting, which needs power. They have gone for substituting in a big way their energy supply using wind energy. In Madhya Pradesh, in certain regions not very far from their plant operation, they have put in windmills which is supplying energy to the grid from which they are drawing power. And there are all kinds of calculations, I am forgetting how many megawatts they are doing. They spent some 20 crores or 25 crores to set up those wind power generation devices. Most of them had to be imported, because we are country, we are still not producing windmills. But they got carbon credit in that process. They had financial gain, so much so that in a matter of a year and a half or so, they recouped that money. So, what they spent in setting up the wind power generation, they got it back, and now say they are going for, they are extending that activity. People talk so much about nuclear power, but people have forgotten that India is a leader in Asia in wind power. We have some about 8 or 9% of our energy demand is being met by windmills. They have certain disadvantages, of course, because it does not ensure a steady power supply to the grid. The power generation changes with seasons. It cannot be done everywhere. It is best where there are high winds, in seashores, on higher altitudes. There are disadvantages, but if we can do it, we not only conserve our coal reserves, we have an alternate source of energy, we get carbon credit. In Denmark, as I mentioned, 50% of our energy supply is coming from wind energy. They are the leaders, but then their energy consumption, total energy consumption is low. So, perhaps India is producing more, even though it is only 8% of the total needs, but there is a good case for going for such alternate energy sources, and the international agreements are pushing for it and giving incentives through carbon credit. Now, I would like to give you some figures for US, not because I am overly fond of US or I want to be too critical, but the Americans have lot of data, reliable data. They analyze their situation time to time. We do not get so much of data reliably for other countries, least of all for India. US is emitting about 6 billion metric tons of CO2 per year, which is a fifth of the total world emission, and their population is far less than one fifth of the world population. They are only 200 or 250 million. The main culprit is not the industry, mind you. There the differences, the distribution is buildings with lighting and appliances 38% of the total energy, transportation, so many cars and vehicles on the road 34%, industrial sector, refineries, paper plants, manufacturing industry, etc., 28%. It does not show agriculture, which is a big consumer electricity in our country, because they run the pump out in water. I do not know how much it is, but it is not shown here. So, again the main metal industry is not that big a culprit. See, globally, even the steel sector is responsible for only about 4 to 6% of global CO2 emission, and the non-ferrous metal industry would be even less. But that does not mean we can be complacent. Everybody has to try his or her best. And please remember, supposing industry takes up these issues seriously and come up with some some technologies, those technologies may find universal application. For example, this ferromanganese industry in Madhya Pradesh, it has gone for alternate source of energy, at least partly they are getting their energy requirement from wind energy. They set a very good example for everybody. Other industries, they set a good example even for the building sector in our country, which is consuming so much of energy. They can think of windmills, and that can have a cascading effect or a multiplier effect. Suppose there is a demand for wind energy, then there will be in our country more and more people trying to make those devices that will wind energy. Mostly these are these huge fans that are fixed to very high poles. You can see them on the Puri beaches. In India, a lot of research has been done, but commercially still not available. We have to go abroad, import from abroad these windmills. Now, see another, there is an important commercial sector, the commercial aviation. It consumes 2% of total CO2, and that is more dangerous because the CO2 that a aeroplane releases is at a higher level. It is in upper atmosphere where it is more dangerous, but the aviation sector is now honor bound to keep it at 2%, even though there can be expansion of the aviation sector. They have said they will find ways and means of operating far more efficiently, so that it does not go beyond 2%. There are many ways of doing it. Many aeroplanes take far too much of fuel because they want to cover long distances, and when they take far too much fuel, huge planes, they become heavier, so they consume fuel less efficiently. So, there are answers to that. Perhaps you have to have smaller planes, smaller distances to fly. There has to be an optimization to that effect, that you are simply not wasting fuel in carrying fuel in your bubbles. So, they have said they will keep it at 2%. We have no figures for the military. In the military sector, the amount of fuel that we consume is enormous, especially when there are wars or battles. But mankind does not have the wisdom. They are not thinking far enough. If they go on fighting and killing each other, and not only they are causing lot of misery to everybody, they are causing lot of global thing also, because whether you are going in a tank or you are going in a military vehicle or you have a plane flying, you are all adding to global warming. Now, what do we do with the CO2 that comes out? Nothing can be done about the CO2 emitted by vehicles. It is going all over the place, you cannot collect. But the subject of sequestration, means collecting CO2, has become in terms of thermal power plants, where there is a stream of CO2 coming out from one place. So, there are now many projects working on how to use that CO2. One idea is to take the CO2 and dump it for storage underground. There are plants already operating, 1 or 2 like that on an experimental basis. The whole idea is to take it about 2 kilometers below the surface, where there is a layer of brine, and at that pressure CO2 would become supercritical. It will dissolve there as a liquid in that brine solution. It will stay there. In future, we might do something about it. There are other ideas I mentioned, is that maybe we can convert CO2 some kind of a building blocks, artificial corals. The best solution people are saying is, you can think of growing bacteria which will convert the CO2 injected into water bodies into food. That algae will grow. That algae can give food, and sometimes they have also grown a kind of algae which secrete oil, which can be petroleum substitute, which means that carbon in CO2 will make a carbon compound which is oil like. So, it will be recirculated. You burn oil, produce CO2, the CO2 will go and through bacterial reaction produce oil again. All such things are in the pipeline, and I am sure 10 or 15 years from now, methods will be found to do something about the CO2 that is causing global warming. But we will not discuss this subject now. Now, here is some data I want to show you, very important, but before that let me go to this. I mentioned about the distribution of energy consumption in the United States. Essentially, there are three sectors: industry, buildings and transportation. Obviously, in our country this transportation sector will be less. We do not have so many vehicles. Our buildings, I think, will be also less, because in most of the energy requirement in their buildings is in heating. In cold climate they have heating devices, and buildings are becoming larger, heating requirements are more, buildings also have many gadgets and appliances, they are consuming electricity. Where are they coming from? Still, if you look at the buildings, petroleum giving 3%, natural gas 12%, coal, thermal power plant 15%, all and building renewables, I do not know what exactly it means, but some nuclear sector is also giving some power to the grids from which the buildings are drawing electricity. Transportation depends mostly on petroleum, 27%. 27% of energy need is by transportation, petroleum, 1% natural gas, some coal, some locomotives and other things. Now, if you go to the industry, renewables, industry coal is giving so much, natural gas is giving 10%, petroleum is giving 10%. In the industry, nuclear power is still not going in, but it is about one third, one third, one third. They can think of CO2 sequestration in the industry, but in transportation the CO2 that comes out of vehicles are so distributed so much over a wide area, because every vehicle is doing something CO2. People say nothing can be done about it unless you make the engines more efficient, or instead of petroleum guzzling cars, go for electric batteries. Batteries come in two kinds, not electric batteries who need recharging, because in that case again you are consuming electricity. Now, there are hybrid cars where a nickel battery self-contained gets charged when the car is running in cruising, and the battery takes over only during startup and acceleration. That is when the pollution is maximum. That is when the battery takes on, and then the ordinary engine runs the car, but then during that process the battery gets recharged. Now, in that process they have seen that pollution is cut down by 90% and energy efficiency is improved by 200%. Means the car can go twice as much distance, pollution would be far less. So, electric hybrid cars in the picture, but in our country some companies have considered options. They are not going for this, they are going for what is known as the devices which will conserve momentum. Suppose a car is going and there is a flywheel which is also begins to move. When the car brakes or stops, all the energy goes into the friction of the brakes or the tire surface. Now, if there is a flywheel and a device that when you are braking, that energy is transported to the flywheel, then when the car stops, the flywheel keeps running. When the car wants to start again, takes the energy from the flywheel, accelerates and moves up. This technology has been demonstrated in our country, but some companies are thinking of going for this device rather than the hybrid cars. Anyway, this is the kind of distribution we have. Now, look at something I wanted to say about America. Here are some data for California, which is the most advanced state in the United States, and the entire country. This side is for here you see the USA, now California consumption, and that side is for United States consumption. We are plotting electric consumption. Now, it is going up in United States, it is going up in California also, and the units are given here, because two things. First of all, population is growing, but more than that they are going to an advanced level of living, their GDP is growing. So, the total electricity consumption is growing. Now, something very interesting is shown here. Look at these two sets of plots. We are plotting figures for United States and California, gross domestic product per capita and kilowatt hours per capita. Kilowatt hours per capita, gross domestic product. This shows that if the GDP has to grow, per capita electricity consumption also has to grow. So, in the United States, you see the GDP is growing, per capita electricity consumption is also growing. But something very interesting is shown in the case of California, that GDP is growing, but per capita energy consumption is not growing. In fact, per capita electricity consumption has remained constant for 30 years in California, although their per capita, but GDP per capita is growing. This only means that state has learned to use electricity more effectively, whereas the rest of United States has not learned that as well. So, their GDP is growing, but per capita electricity consumption is not growing, because they are going for more and more efficient technologies. This actually they call it the Rosenfield effect, that the average Californian uses less electricity than a typical person uses in the rest of the country. The gap has gone wider over the past 30 years, even though California has become relatively more wealthy. Now, the message I want to give it, that if you are in an industry, the industry can grow, not necessarily consume more energy. It can grow consuming perhaps the same at the same energy level consumption, provided it takes care to introduce more energy intensive devices, or cuts down on energy wastages, or has provisions to recoup the energy from the waste energy, either from the hot discharges, hot gases, or from the exothermic heat of reactions. So, there is tremendous scope of energy saving in industries. I will come back to non-ferrous metallurgy now again. Now, before we want to talk about energy saving in a non-ferrous metal industry, first thing we have to do is to analyze, do an audit, find a method of knowing what really is the energy consumption in a extraction process. I have started my lectures right in the beginning by giving an example of aluminothermic reduction, that you can take an oxide, and if you reduce by aluminum, it is an exothermic reaction. So, one is may be tempted to think it really needs no energy, because if there is sufficient heat coming out, it goes on its own, you do not have to supply external energy. It is what we can call an autogenous process, and when we were students, we were actually told that aluminum reduction is very good from energy point of view, because you do not need energy supply. It is only later I learned it is wrong. If you really look at the thing holistically, you would know it is not that you are not using energy, because after all the aluminum that you are using has consumed a lot of electricity when it was produced. That is what leads us to the concept of process fuel equivalent or PFE, which is calculated by taking into account the energy equivalent of raw materials that have gone in, the energy required for the process to happen, minus whatever energy that is generated in the process, minus whatever energy you can recover from hot gases and hot liquid discharge or gases, whatever. So, there are ways and means of finding energy during the process or after the process, but take into account not only the energy you have to supply either as a fuel or as electricity for the process to happen, but also the energy that was consumed in making raw materials. Taking all this, we calculate process fuel equivalent. This concept was first emphasized by Kellogg, and I have given a reference. It is as old as 1974, but the concept continues. Now, here are process fuel equivalents for different metals, and some figures are quite interesting. In the iron production, where we have blast furnace, oxygen, steel making, that is a pyrometallurgical route, product steel ingot, process fuel equivalent is 22 gigajoule per ton. So, from the starting from the raw materials up to the product per ton, this is the fuel requirement. You have taken out whatever energy you could get from the system, from whatever energy was required in production of raw materials as well as in carrying out the process. Lead blast furnace, that is blast furnace, dross, fire refine, all that pyro process, refined lead up to 23. So, iron and lead from energy point of view are almost equal. The worst culprit is aluminum. If you consider Bayer-Leach process, Hall-Herold's process, hydro, all the hydrometrical shape, to give you aluminum ingot, it is 280, more than 10 times iron and lead. Copper. Now, copper is very interesting. You know, copper, everything is exothermic, sulfides are you are roasting, generating heat, this and that, but you are consuming energy in the flotation cells. There is lot of energy loss from the pyrometallurgical steps. So, energy supply is required. So, if you take all that into account, to produce copper cathode, it comes to 100, especially because there is an electrolyte. I still have not brought in electrorefining, mind you, copper cathode. Yes, electrolytic process is included, that is why it is high. If you go for special high, this I do not understand what is there. In the case of zinc, roast, leach, electrowinning, it is around 55. So, the worst culprit from energy point of view is aluminum, then comes copper. How do we recycle energy? That is a question of vital importance in industries, because if you recycle energy, your net energy consumption will be low, and if that is low, you will save in the energy cost. You will also release less CO2 to the air, atmosphere will be cleaner, and from the point of view of industrial metabolism, where the idea is to dematerialize, means use less input and less output, everything is favorable. Now, energy considerations have led many technological and resources management innovations, including recycling. In this section, we will briefly discuss some issues regarding potential energy savings through recycle and reuse. I am going to give you some examples. Many producers are not simply interested in a product that saves most energy if recycled, but rather in a product that has the lowest overall impact. I mean, we need to look at from environmental point of view also. In some situations, product reuse or material substitution may be more desirable than recycling. From an environmental perspective, energy savings are only one of several considerations. In many cases, there is a trade-off between reduction in energy consumption and that of water and air pollution, as well as in generation of solid hazardous waste. We have to optimize. The actual impacts on the environmental will vary with population density, available fuel sources, transportation, infrastructure and other factors. So, it is a very complicated thing. We cannot only say that we must use less energy. If you try to do that, there may be some other adverse effect. So, you have to have a holistic view. Now, I have given you some figures on process fuel equivalent. Let us consider some figures for straight energy requirement, forget about PFE. Energy required for production of metals from their respective ores and secondary sources. We are not talking about now PFE, just energy for the processing step. Now, magnesium from primary ore is 358 kilojoule per ton. This is 10 to the power 6, we must make it 10 to the power 6 kilojoule. From primary ore is 358, very high, but for secondary scrap it is so low, because secondary scrap is where everything has almost been done. So, energy savings from recycling will be very high, almost I mean nothing is there in the secondary metal energy requirement. Aluminum primary 244, from secondary 12, this is much saving. Nickel primary from ore, from nickel scrap, this will be the saving. Copper, this will be the saving. Zinc, this will be the saving. Steel, this will be the saving. Lead, this will be the saving. The saving is less in the case of steel and lead, because to start with they did not require so much of energy in production. But in all these cases, especially where there is an electrolytic step, enormous amount of energy saving is there if we can recycle the scrap. So, we can say obviously recycling not only saves energy, but it solves an environmental problem. This has become an integral part of many industries in the advanced countries, where huge amounts of scrap are readily available. Let me give you some definitions again, something related to recycling. There is no widely accepted definition for the term recycling. Although we use it very loosely, there is no precise definition. Different people have adopted different definitions to suit their needs. For example, incineration to recover energy is considered to be a form of recycling by some people. Say the municipal garbage that accumulates in homes. In many cities, all that garbage is collected, sorted out. They remove plastics, glass, some other perishables. They with paper and things like that are easily combusted, they are incinerated, and when you get an energy, they say they have recycled the material, because from the waste they have got energy, but some people do not consider it to be recycling. From an environmental point of view, the recycling of material displaces the need for extraction of virgin or primary resources. Some people say the recycling should really imply that you are doing something about the primary resources, you are increasing its life. In practice, however, any secondary use of material is often considered recycling. So, if you have produced something, if you can find another use of it, which means you do not need material to produce that from fresh resources. So, that some people consider recycling. Significant amounts of scrap that accumulate in the initial production process of smelting or milling is known as industrial or home scrap. In any plant, not everything that you have produced goes for final product. You will find there will be some intermediates which are lying here and there, that we will call industrial or home scrap, that can go back again in the production step. Such materials are generally sent to a separate facility to be cleaned, cut, shaped, rolled and finished. Most scrap generated in this stage is referred to as prompt industrial scrap. So, the scrap is generated within the plant, that can be very easily recirculated. Okay. Being clean, these two types of scrap are usually incorporated into the furnaces in most industries. Products sold to customers invariably become unusable after a lifetime and are discarded. These, when collected for the purpose of manufacturing of new products, are called post-consumer or old or obsolete scrap. Since this scrap lies scattered, it generally presents difficulties in way of collection and reuse. However, with improved collection systems, more and more old scraps are being recycled. It is estimated that by the year 2010, 75% of the 400 to 500 million ton of total scrap consumed will consist of obsolete scrap only. Now, coming back to again energy consumption in general, let us talk about one industry, the average energy consumption for mining, beneficiation, smelting, refining of copper, where we start off with 0.55% copper grade. That is by flotation upgraded, and it goes for different steps, roasting, smelting, converting. 40% of energy in the copper industry goes for beneficiation step, because you are getting a concentration from such a low grade ore, and whatever you do, flotation process or whatever, there will be energy requirement for operating those facilities. Mining requires about 20%, smelting and refining requires this. So, if we talk about energy saving in the copper industry, we simply cannot talk about smelting, converting, roasting, etc. We have to do an energy audit of the whole system. We have to have a review of the entire system, and you will find if you really want to save on energy, you have to look at the mining side also, because perhaps there may be more scope there. It may be easier to save energy in the mining sector than in this sector. If something can be saved in this sector, then in the mining sector we do, but chances are from mining to beneficiation that there will be more scope. So, we have to see that. So, we say the third column represents the best possible industrial energy consumption data. No, this is coming next. Now, here is some industrial energy need for metallurgical production of 1 ton of primary metal, and just a comparison. Aluminum needs most metal, most energy. Then you have zinc copper, lead, iron. Now, all the metallurgical reduction processes for the big four non-ferrous metals aluminum, zinc, copper and lead, the lead metallurgy is the least energy consuming process, followed by zinc pyrometallurgy. The most energy wasting processes are the classical pyro, hydro and electrowinning of copper. Hence, there is ample scope to narrow the gap between the theoretical and practical energy need. Now, this is there far too much of data here. So, I think I will read it for you. The data are not important, but there is a fundamental thing inside this in this table that you should understand. You know, when we extract a metal from an ore, essentially we try to upgrade the ore to a concentrate. Ideally, we should get a pure mineral, and if we had a pure mineral available, then the energy that should be required should equal the free energy of formation, because some energy is required for formation of the mineral. So, we can decompose the mineral using that same value of free energy of formation. It should be equal to free energy of decomposition. Why is it that we need lot more? Because first of all, we do not have a pure mineral, and secondly, to come to that mineral, we have to come through beneficiation steps. We are starting with a poor grade ore and coming not again to something which is almost pure mineral, but it is close to that. But it is we need lot of energy in upgrading the ore, and that is why we need so much more energy. Now, let us see how it is here. You see, titanium sponge production needs so many kilowatts hour per ton. Okay. But actually, free energy formation, if you go, it will be only 4.7. There are two sets of figures. What these are, I will explain later on. Magnesium ingot production takes 99.9 kilowatt hour per ton, but really free energy of formation is so much smaller. But if you come to lead, its free energy of formation value is low, it requires less process energy also, because it is not consuming so much of energy in upgradation. I will look at this table once again. The reference is here. I think something has been typed wrongly. I will get it corrected after this lecture. And if you see the book, there is a lot more discussion on this, but essentially what I am trying to say, that we cannot take the free energy of formation as a guide to find out in practice how much of energy it will require for decomposition, because for actual process we need a lot of energy to prepare the ore to bring it to a stage from where the decomposition will be done either pyrometallurgically or hydrometallurgically or electrometallurgically to separate out the metal in elemental form. So, this is important, that considerable gap exists between the theoretical energy required for extracting a metal from its mineral and the actual energy requirement for winning it for its available ore, from its available ore. This is because ores and minerals contain a lot of gangue which consumes considerable energy during processing. With the many unit operations involved in minerals and metal processing industries, several several of which require significant inputs of energy. This industry has experienced substantial increase in percentage of total cost of energy alone. So, initial steps cause too much of energy. Here is some data to substantiate what I am saying, that energy consumption, distribution, processing of copper sulphide ore, unit operation and energy distribution percentage. In copper sulphide ore processing, 73% is going into crushing and grinding. Something we very often forget how energy consumption this is, that what we have extracted, mined, it has to be first crushed to a smaller particle size, then ground, and for flotation it has to be ground to very fine size, minus 300 mesh. Then flotation cells operation requires some energy, filtration some, water cycle and review water. So, it is the initial steps which have consumed large amount of energy, and that is why even if there is a mineral which is not so stable, you need a lot of energy, because to come to that upgradation of the ores you have done so much. Now, we will now quickly discuss approaches to energy saving. The potential of energy saving are in many areas: control 10 to 15%, optimization 20%, grinding aids 10%. Flotation energy requirements can be reduced by employing the larger volume flotation cells that are presently available. It has been shown that 10% energy savings can be achieved by increasing the cell volume by 50 to 80%. You go for a bigger flotation cell, it will consume less energy. When wet solids are to be thermally dried or subjected to an endothermic reaction such as calcinations or disposed for landfilling, where a transportable or handable material is essential, then mechanical dewatering should be considered. So, dewatering itself is an energy consuming process. There are many techniques. One can employ a device like a filter, belt press or centrifuge. There are now many new solid liquid separation methods that offer potential energy savings as well as other cost reduction elsewhere. Some of these are listed here: steam drying, use of surfactants, especially chemicals, high pressure filtration, improved thickening methods, electrophoresis, all kinds of things. So, technology is advancing, newer things are coming, there is tremendous scope for energy saving. I will continue this discussion and try to solve one or two very common sense problems little later. Thank you.